This is Physics 2120, Lecture 26. Today we're going to start talking about image formation. In particular, we're going to look at image formation by mirrors. So there's some notation that we need to understand for both mirrors and lenses. And the first is an object distance, and that is the distance from the object, whatever we're trying to image. So from the object to the mirror, or from the object to the lens, and we're going to denote it with the variable p. The image distance is the distance from the image to the mirror or lens, and we denote that with q. And then lateral magnification of a mirror lens is the ratio of the image height to the object height, and it's denoted with a capital M. Now, images are always located by extending diverging rays back to a point from which they intersect. Images are located either at a point from which the rays of light actually diverge or from a point from which they appear to diverge. A real image is formed when light rays pass through and diverge from an image point. Real images are things that can be displayed on a screen, whereas a virtual image is formed when light rays don't actually pass through the image point but only appear to diverge from that point, and virtual images cannot be displayed on a screen. So the easiest mirror to start looking at is a flat mirror. So I have some object here, and I have light rays come out of the object. And as they hit the mirror, every ray is reflected from the mirror following the law of reflection. So that as they come off and hit our eye, the light rays are going to appear to have come from this point over here, the image point. This is a virtual image. The light rays don't actually come from eye, they're coming from the object, but they appear to have come from there, and so we see that image actually behind the mirror. A flat mirror always produces a virtual image. And we can use geometry to determine the properties of the image. There are an infinite number of choices of direction in which the light rays could leave the point on the object. But we need at least two rays to determine where an image is formed. So one ray is always going to start at point P, travel to Q, which is the mirror, and it reflects back on itself. So we follow this ray, comes straight to the mirror and straight back. The other ray follows a point from P to another point on the mirror, and as it's reflected away, it appears to come from this point. So the triangles PQR and P'QR are congruent. So to observe the image, the observer would trace back the two reflected rays to point P'. So point P' is the point where the rays appear to have originated from. The image formed by an object placed in front of a flat mirror is as far behind the mirror as the object is in front of the mirror. In other words, the value of P is equal to the value of Q. The lateral magnification M is defined as the image height over the object height, or H' over H. And this is the magnification for any type of mirror. It's also going to be valid for images formed by lenses. Magnification does not always mean bigger. The size can either get larger or smaller. So M can be less than or greater than 1. Less than 1 means the image is smaller than the object. Greater than 1 means the object or the image is larger than the object. The lateral magnification for a flat mirror is 1, which just means that H' equals H for all images in a flat mirror. The image size or the image height is exactly equal to the object height. Now, one of the things that we see in a flat mirror is an apparent left-right reversal. For example, if you raise your right hand in the image, you see it as a left hand. The reversal is not actually a left-right reversal. It's actually a front-back reversal. It's caused by the light rays going forward through the mirror, then reflecting back from it. So the image is as far behind the mirror as the object is in front. The image is unmagnified, so h prime equals h, or m equals 1. The image is going to be virtual. I can't project it on a screen. It appears to come from behind the mirror. The image is upright. In other words, it has the same orientation as the object, but there's a front-back reversal in the image. Now we can do some interesting things with mirrors. Have you ever wondered how the day-night settings on an automobile mirror works? And the way it works is the reflecting side of the mirror behind the glass is actually behind the piece of glass that is not the same thickness at both sides. So in the daytime setting, the incident light coming back comes in, is refracted on the glass, hits the mirror, comes back out, and comes into your eye. Where on the nighttime setting, we tilt this a little bit, and when we tilt it, the incident rays come out and would come out above your eye. However, we know that at the front of the glass, there's always some reflection, and so we're just looking at the reflection off the front of the glass. Most of the light continues through, so we see a very dim image as it comes from the reflected off the front of the glass. Now the next mirror we want to look at is a spherical mirror. And it has a shape or section of a sphere. And the mirror is going to focus the incoming parallel rays to a point. A concave spherical mirror has the silvered surface of the mirror on the inner or the concave side of the curve. Or in other words, if I were to draw a mirror, a concave would be on this side of the mirror. The convex spherical mirror has the silvered or reflecting surface on the outer part, or in other words, it would be on this outer part of the mirror. So some other notations with a concave mirror is that it has a radius of curvature r. Point C is called the center of curvature, and point V is the center of the spherical segment. And the line that goes from the center of curvature to the center of the spherical segment is called the principal axis, or the optical axis of the mirror. Now, we only use rays that diverge from the object and make small angles with the principal axis. Those are called paraxial rays, and paraxial rays reflect through the image point. One of the problems with a spherical mirror, though, is something called spherical aberration. An aberration is a distortion in the image. So rays that are far from the principal axis converge at other points on the principal axis, and it produces a blurred image. So, for example, light rays that come off here come back and focus at this point here, but light rays that go far from it, the axis, focus at a different place. So if I'm trying to look at this or project this on a screen here, I'm going to get a blurred image as I get different light focusing at different places. Now we can use the geometry to determine the magnification of an image formed in a concave mirror. Magnification is going to be h prime over h, which, looking at the similar triangles, is also minus q over p. Remember, q is the distance from the mirror to the image, and p is from the mirror to the object. Now, h prime is negative when the image is inverted with respect to the object. So in this case, h is upside down from the image, so since it's inverted, h prime, whatever that value is, would be negative. The geometry also shows that there's a relationship between the image and object distances. Specifically, 1 over p plus 1 over q is equal to 2 over r. It's called the mirror equation. So if P is much greater than R, then the image point is halfway between the center of curvature and the center point of the mirror. In other words, as P goes to infinity, 1 over P goes to 0, and so Q is equal to R over 2. The image point is half the radius. So when the object is very far away, or when P approaches infinity, the incoming rays are essentially parallel. And in this special case, the image point is called the focal point. And the distance from the mirror to the focal point is called the focal length of the mirror. For a spherical mirror, the focal length is half the radius of curvature. So if I look at these beams of light coming on this spherical mirror, the colored beams are traveling parallel to the principal axis. The mirror reflects all 3 beams to the focal point. So the focal point is where they all intersect. In this case, it's the white point, as the red, green, and blue light are all interacting. The focal point is dependent solely on the curvature of the mirror, not on the location of the object. It also does not depend on the material from which the mirror is made. The focal length, or the focal point, F, is R over 2. So then the mirror expression can be expressed as 1 over P plus 1 over Q is equal to 1 over the focal length. Here's another picture showing a spherical mirror as parallel light rays come, and as they come, they all are reflected to that similar point, which we call the focal point. A convex mirror is sometimes called a diverging mirror. The light is going to reflect on the outer convex side. The rays from any point on the object diverge after reflection as though they were coming from some point behind the mirror. So the image is virtual because the reflected rays only appear to originate at the image point. So if we look at a ray diagram and look how an image is formed by a convex mirror, again we have a light rays that come straight out along the axis and would reflect out. We have one that goes towards the center of curvature and reflects back out. And all we need is those 2 rays to see where they appear to diverge from. So this is a virtual image. In this case it's upright and it's smaller than the object. So we need some sign conventions to denote whether P or Q are positive. And these are going to apply to both concave and convex mirrors. The equations used for the concave mirror also apply to the convex mirror. So, if we're on the front or the real side, P and Q are positive for the incident and reflected light. If we're on the back side or the virtual side, P and Q are negative. And there's no light actually on the back side. So, P is positive. The object is in front of the mirror. It's a real object. It's negative when it's in back of the mirror. A virtual object. We haven't talked about virtual objects yet, but you can have from other optical instruments a virtual object on something, and we'll get to some problems like that later. The image location, Q, is positive if the image is in front of the mirror. It's a real image. It's negative, it's a virtual image, or it's behind the mirror. Image height is positive if it's upright, negative if it's inverted. The focal length is positive. The radius is positive if the mirror is concave. It's negative if the mirror is convex. And magnification will be positive if it's upright, negative if it's inverted. So a ray diagram can be used to determine the position and size of an image. These are graphical constructions which reveal the nature of the image. They can also be used to check the parameters calculated from the mirror and magnification equations. To draw a ray diagram, you need to know the position of the object and the locations of the focal point and the center of curvature. And we're going to draw 3 rays, and all are going to start from the same position on the object. And the intersection of any 2 of these rays at the point locates the image. And the 3rd ray is just going to serve as a check on how we constructed it. So ray 1 is drawn from the top of the object parallel to the principal axis, and is reflected through the focal point. Ray 2 is drawn from the top of the object through the focal point and is reflected parallel to the principal axis. Ray 3 is drawn through the center of curvature and reflected right back on itself. Now, the rays actually go in all directions from the object, not just those three special ones that we've chosen. But those are chosen because of the ease of construction. And the image point obtained by the ray diagram must agree with the value of Q calculated in the mirror equation. So, looking at the ray diagram for a concave mirror, where the object is outside of the radius of curvature of the mirror. Ray 1 is drawn parallel to the optical axis and down through the focal point. Ray 2 is drawn from the top of the object through the focal point and reflected back parallel to the optical axis. Ray 3 is through the center of curvature and is reflected back on itself. And all three of these cross at the same point. So the center of curvature is between the object and the concave mirror surface. The image is real, in other words, it's in front of the mirror, I can project it on a screen. It's inverted, and it's smaller than the object, it's reduced in size. Now I can also have a concave mirror where the object is between the focal point and the mirror, or P is less than F. We do the same thing. In this case, ray 1 is drawn from the top of the object and is reflected through the focal point. Ray 2 is drawn from the top of the object through the focal point, or in other words, in this case, it's going to look like it's coming away from the focal point, then parallel to the optical axis. Ray 3 is drawn as if coming from the center of curvature, reflects right back through the center of curvature. Now, in this case, these three rays are diverging, and they appear to come from a point behind the mirror. So the object here is between the mirror surface and the focal point. The image is virtual. The light rays don't actually cross at any point. They just appear to come from a point behind the mirror. The image is upright and is larger. Now, for a convex mirror, ray 1 is going to be drawn from the top of the object parallel to the principal axis as are reflected away from the focal point. Ray 2 is drawn from the top of the object toward the focal point and is reflected parallel to the principal axis. And ray 3 is drawn through the center of curvature on the back side of the mirror and reflected back on itself. So again, we can look at this convex mirror. Ray 1 from parallel to the optical axis and then is reflected as if coming from the focal point. Ray 2 is drawn from the top towards the focal point, but then when it hits the mirror is reflected back parallel to the optical axis. And ray 3 is drawn towards the center of curvature and is reflected back on itself. And again, rays 1, 2, and 3 all are diverging, and they appear to be diverging from this point behind the mirror. So the image is virtual, the image is upright, and the image is smaller than the object. So with a concave mirror, the image may be either real or virtual. If the object is outside the focal point, it's real. If the object is at the focal point, the image is actually infinitely far away and we don't get an image. And when the object is between the mirror and the focal point, we get a virtual image. With a convex mirror, the image is always virtual and upright. As the object distance decreases, the virtual image increases in size. So let's work an example problem with a concave mirror. Assume that the spherical mirror has a focal length of plus 10 centimeters. Locate and describe the image for object distances of 25 centimeters, 10 centimeters, and 5 centimeters. So we can use the mirror equation. 1 over P plus 1 over Q is equal to 1 over F. In this case, we want to know Q. So 1 over Q is 1 over F minus 1 over P. So Q is 1 over 1 over f minus 1 over p, and we plug in our values, and we get q is 16.7 centimeters. So the magnification is minus q over p, minus 16.7 over 25, or minus 0.668. So if this is the case, the image is smaller, and it's going to be real, and it's going to be inverted. Now, what about at 10 centimeters? So 1 over q here now is 1 over 10 minus 1 over 10, which is 0, which means q is infinity. That means there's no image formed. So as I put it right at the focal point, it's hard to show in this picture, but essentially the image is infinitely large and it is infinitely far away. When p is equal to 5, then q turns out to be minus 10 centimeters. So the magnification is minus q over p, so it's going to be 10/5 or 2. So in this case, the image is going to be virtual, it's going to be upright, and twice the size of the object. Let's look at another problem. An anti-shoplifting mirror shows the image of a woman who is located 3 meters from the mirror. The focal length of the mirror is minus 0.25. The minus sign tells us it's a convex mirror. Find the position of our image and the magnification of the image. So again, q is the inverse of 1 over f minus 1 over p. So we plug that in. That's 1 over minus 0.25 over 1/3. And turns out q is minus 0.23 meters. The magnification then is minus q over p. And so that turns out to be 0.077 or 0.08. So it's a virtual image because it's a convex mirror. It's going to be smaller and upright. The positive sign tells me it's upright. So let's review. We talked about image formation. We talked about flat, convex, and concave mirrors. The most important equation that we introduced today is the mirror equation. 1 over p plus 1 over q equals 1 over f. And then we talked about how to find images and the properties of the images using ray diagrams.